Welcome back. In the last lecture, we studied the rotational flows. The flow is said to be rotational when the vorticity omega, that is the curl of velocity, is zero everywhere. The circulation around any arbitrary loop in an irrotational flow is zero, provided that the loop is reducible. If an inviscid fluid is initially irrotational, then it remains irrotational at all subsequent times. We had seen that the governing equation for irrotational flow is the Euler equation given as del V by del T plus V dot del V is equal to minus G delta Z minus del of P by rho. The last two terms combine to give minus del of G Z plus P by rho. Using the vector identity A cross B is equal to A dot del B minus A dot del B, we get V cross omega is equal to V dot del V minus 1/2 del V square for A and B is equal to V. Then we get from this V dot del V is equal to V cross curl of V plus 1/2 delta V square. And using this in the governing equation, we get del V by del T plus V cross omega is equal to minus del of Gz plus P by rho plus V square by 2. Thus, if the flow is rotational, that is, if omega is equal to 0 and the flow is steady, the left hand side is 0 and we get minus del of Gz plus P by rho plus V square by 2 is equal to 0. Thus, the Bernoulli equation holds everywhere in a steady irrotational flow and not just on a streamline. We can take point 1 and 2 for Bernoulli equation anywhere in the flow field and not just on a streamline as was required for general inviscid flow, which were not necessarily irrotational. We again start with the last form of the Bernoulli equation and taking the curl of this equation, we get del omega by del T plus V dot del of omega is equal to omega dot del on V. The first two terms that are the terms on the left are combined to give you the substantive derivative of omega with time is equal to omega dot del V. This is known as the vorticity evolution equation. If omega is 0 initially in an inviscid flow, then d omega by dt is equal to 0. D omega by dt is equal to 0 means that the substantive derivative of omega is 0. And since omega was 0 to begin with, the value of omega is 0 at all subsequent times. That is, an irrotational flow remains irrotational flow at all subsequent times. The vorticity omega, which is the curl of V in a rotational flow, is 0, and the circulation gamma about any reducible circuit lying entirely in the rotational field is also 0. Let us consider a circuit as shown. The integral V dot ds over this circuit A, B, C, D, A going around counterclockwise is the integral of V dot ds over the arm ABC plus the integral over the arm CDA. We can reverse the direction from CDA to ADC to get the circulation about the whole circuit as integral integral of V dot ds over ABC minus the integral over the path ADC. Therefore, the integral about this path ABC is the same as the integral about ADC. Since we have taken path arbitrarily, this means that the integral of V dot ds between any 2 points A and C is independent of the path that we take. Thus, they depend only on the location of the endpoints A and C, so that we can write integral of V dot ds from A to C is equal to some function of C minus that function of A. Depends only on the locations of the endpoints, not on the path. This is possible only if V dot ds is d phi, that is del phi dot ds. That is, we can write the velocity as the gradient of function phi, so that the velocity in any direction is del phi by del s is equal to del phi dot ds. The function phi is called the velocity potential, and the velocity components in the various coordinate systems can be found out. The velocity components in rectangular coordinates are given by u is equal to del phi by del x and v is equal to del phi by del y. Also given in this table are the velocity coordinate u and v in terms of the gradient of the stream function psi that we did earlier. U is equal to del psi by del y and v is equal to minus del psi by del x. Similarly, we can write the velocity components in the cylindrical polar coordinates. We have done this for two-dimensional flows. These can be done for three-dimensional flows as well. The continuity equation is del dot v is equal to del u by del x plus del v by del y is equal to 0. The two components of Euler equations for the incompressible and steady flows are given below, and these are to be solved subject to boundary condition that the normal component of velocity is 0 at the wall. As was discussed earlier, we cannot apply the no-slip condition at the wall. If the inviscid incompressible flow is rotational, the continuity equation above results in del square phi by del x square plus del square phi by del y square is equal to 0. This is obtained by substituting del phi by del x for u and del phi by del y for the velocity component v. In vector notation, this becomes del square phi, the Laplacian of phi is equal to 0. This is the well-known Laplace equation to be solved with del phi by del n is equal to 0 at the walls. Notice that this equation, though difficult to solve, is no longer coupled to the Euler equation. The flows in which we can define the velocity potentials and which are therefore called potential flows can be obtained simply as the solution of the continuity equation, which reduces to the Laplace equation subject to the boundary condition that the normal gradient at the boundary is 0. Physically, this means that there is no flow into the wall or out of the wall. The wall is impervious. The lines of constant velocity potentials are called potential lines of the flow. In two-dimensional, del phi, in two dimensions, d phi is equal to del phi by del x into dx plus del phi by del y into dy. And recognizing that del phi by del x is u and del phi by del y is v, we get d phi is equal to u dx plus v dy. Thus, the slope of a line of constant potential is dy by dx is equal to minus u by v. The negative of the x component of velocity divided by the y component of velocity. Recall that the streamlines, which are the lines everywhere tangent to the velocity, the slope of those streamlines is given by dy by dx is equal to v by u. Since the slope of potential lines has been found to be minus u by v, this means that the potential lines, which are the lines of constant potential phi, are perpendicular to streamlines, which are the lines of constant psi, except at the stagnation point. Thus, the streamlines are perpendicular to the potential lines at every point of the flow field. This is called flow net in some texts. And from this, we get del phi by del x is equal to del psi by del y, and del psi by del x is equal to minus del phi by del y. If we define a complex variable phi plus I psi, real part phi and the imaginary part psi, the stream function, then these two conditions are nothing but the Cauchy-Riemann conditions applicable for analytical function of a complex variable. Therefore, psi and phi, when they combine to form a complex variable phi plus I psi, this complex variable is an analytic function of z, which is x plus I y. This property of the potential and the stream function, which is given the name complex potential, is exploited in finding out the solutions of the Laplace equation. We will not do this here in this elementary course. To summarize the velocity, potential, and stream function once again, the definition of potential function is that V is equal to del phi. For the stream function, it is V is equal to curl of psi. The continuity requires the potential function to be del square phi is equal to 0. This requirement is built in into the stream function. The requirement of irrotationality is built in the potential function. But for the stream function, it becomes del square psi is equal to 0. So both phi and psi satisfy Laplace equation. Given below are the velocity components in the rectangular coordinates and in the cylindrical polar coordinates. Same as before. Let us point out some interesting consequence of the fact that the velocity field of a potential flow is determined fully by the Laplace equation. First, the equation and boundary conditions are valid for both steady and unsteady flows, even though the time variation does not enter the equations explicitly. Interesting. If the boundary conditions are changing at time, the solution also changes with time. The rate of change of boundary condition does not affect the solution at a given time. This means that the solution is quasi-steady with every point in the flow field responding immediately to any change in the boundary conditions. This is the consequence of flow being incompressible, which requires that the disturbance propagate at infinite speed. The second interesting consequence is that the velocity field can be obtained independently of the pressure field, but not vice versa. We cannot solve the Euler equation to obtain the pressure field without knowing the velocity field. But we can solve the Laplace equation to obtain the velocity field without dealing with the pressure field. The Laplace equation for potential flow is purely a kinematic equation, while the Euler equation is a dynamic equation. Thus, the pressure gradient adjusts itself depending upon the inertia of the fluid measured by the density rho to give the desired velocity gradients. The third important property of the potential flow is that the Laplace equation and the relevant boundary conditions are linear, and therefore it is possible to build up solutions to complex flow fields using superposition of simple flows. Since the equation as well as boundary conditions are linear, we can take a number of elementary flows and simply add the potentials of those flows, and the sum would satisfy the Laplace equation.